Hi, welcome to Mat210 Calculus. In this lesson, we're going to talk about 3.5. And these are two derivatives we occasionally use, but not as much. A to the x, where a is actually a number, some number raised to the power of x. And the other one is log to some base other than, it could be base 10 or base 7 or whatever of x. So these have two unique, we could say derivatives or formulas. So let's look at the first one. If y equals a to the x, then the derivative of that is going to be the natural log of a. Remember, a stands for a number times the original problem, a to the x. So let me give you a few examples. Let's say y is 2x, 2 to the x. Then y prime is going to be the natural log of the number 2, which you could look up on your calculator, and that times 2 to the x power. Kind of a weird one, huh? And that's all there is to it. Okay, what if you had y equals 1.4 to the x? Well, y prime is going to equal the natural log of 1.4 times 1.4 to the x. So nothing outstanding about this formula. It's just kind of plug it into a formula. Here's a little bit tougher one, 3 to the 2x. Okay. So I would assume this is the natural log of the number times 3 to the 2x, the original problem. But I would imagine we would still have to do a chain rule on this. So we have to take the derivative of 2x, which would be 2. And I guess you could just leave it like that, or you could rearrange it. Maybe write it as 2. Let's put equals. Let's put our derivative down, 2. 2 ln 3. There really is no specific way you have to write this. And that's it. So something you might want to practice on. It's one that's, to me, it's hard to remember, right? Because we don't use it that often. I have to look it up every time. Okay, how about the log of a to the x? Y equals the log, and this could be a again stands for a number any base to the x power. So we're taking the log of something to a base. And derivative of this is going to be 1 over the natural log of whatever this number is times 1 over x. The log of x is 1 over x. And then it's kind of 1 over the natural log of the base times 1 over x. So let me give you this one. What if they just gave you y equals log x? Okay, when we have a situation like this, and we don't have a base, we're going to have to assume that the base is 10. If it's not written, we're assume it's 10. So this would be 1 over the natural log of the base times 1 over, if this was a number, it would be 1 over that number, or 1 over, in this case, x. That's all there is to it. Okay, what if y equaled 1 over, equals log base 8x, or base 8. Well, y prime, again, I should write y prime. Y prime is 1 over the natural log of the base times 1 over this x. Okay, the book says, well, what if we got something a little bit more complicated? What if we had something like y equals log base 3 of x squared plus 1? Kind of like this problem, a little bit more advanced. So y prime, let's go over a little bit, is 1 over the natural log of 3, right? Times 1 over this quantity, plus I would assume now we have to do chain rows. So we got to take the derivative of the inside of the parentheses, which would be 2x. And that would be your answer. Or you could just kind of simplify it to 2x over natural log of 3 times x squared plus 1. Maybe something like that. So you can see it's just it's basically formula driven. I did notice that there was one in the book that was kind of interesting, and this was number. Let's try one here. Let's see if we got anything more complicated. Oh, we got this one D in the book. They have this problem. Function of x. Okay, we got a little bit different start here. Equals, let's see, x cubed log base 5 x. So this looks like a little bit of an ABBA action, you know. This is A and this is B. A, B prime plus B, A prime. So let's see what the derivative would be. See if I can set this up a little bit so you can see it better. Here we go. All right, so it would be A times the derivative of B. Well, this would be 1 over what? The natural log of 5 times 1 over x. So it's A times the derivative of B plus B. So we're not going to do anything to this mess. Times the derivative of A, which would be 3x squared. So I don't know what else they could do to this. What they could do is this x cubed and this x could be reduced. Let me do that with another colored pencil here. We can maybe cross this off and change this to x squared. Sometimes they reduce these and sometimes they don't. So we kind of canceled this and we canceled this out a little bit. And we could factor out, you see this term, there's 2 terms here, separated by an addition sign. So it looks like we could factor out an x squared out of both of those terms. X squared, let's put a bracket here. This would be 1 over the natural, let's see, this x is gone. So it's just 1 over the natural log of 5 plus, we could take out the x squared, so we could probably write this as 3 log base 5x. So we can put it in a more simpler form, but that's pretty much it. So this is an ABBA. I did come across one other problem that was kind of interesting. This was number 33. I wrote it down here so we have it handy. Let's flip this over. 33. You had 7x times the log base 4 of x to the 9th power. Okay, so this one looks kind of interesting. Let's zoom in a little bit more into it, make it more exciting. Let's see what we can do on this one. So this is an ABBA, A. And it's kind of funny because this is an ABBA, but they kind of switched around and did this part first and then this in the answer in the back of the book. So but we'll go ahead and try it. Okay, this is A, didn't do anything to it, times the derivative of B. Well, here we have a 9. So I think they're going to handle this as just a regular, problem. If you had x to the 9th, that would be 9x to the 8th. So it's going to be 9 parentheses log base 4 x to the 8th, okay? Times the derivative of the inside, which would be 1 over the natural log of 4 times 1 over x. So that has, we're going to have to handle it like a regular. So we're going to do the power on the outside. We're going to use chain rule. Power on the outside and then power in the inside. So we're going to do that plus this expression, log base 4x to the 9th. Nothing doing there, times the derivative of 7x. So let's see if we can remember what that one was. We just did it. It's the natural log of 7, the natural log of the number times the original problem, 7 to the x. So that's a new one we just learned today. Both of these are new, actually. Okay, so basically the book just left it in that order. Okay, they just kind of rewrote it. I don't know what they somehow in the back of the book they put this first and then this. Personally, I don't know why. Maybe they wanted it in descending order, so they wrote it like this, which kind of was throwing me off, when I was trying to look at it. They wrote it as 7x ln x, something like this, log base 4x to the 9th plus, and then they wrote the other part as 7x. Well, actually, they probably put the 9 first and then the times the 7 to the x times the log base 4 x to the 8th. And then they put this over natural log of 4 and x. Okay, something like that. So they might have had it switched around a little bit or something like that. I don't know. But that's basically the answer they gave. Why they didn't factor this out and this out, I don't know. I probably would have factored those two things out. Personally, I would have left it as the natural log of x times the log base 4 of x to the 8th times, put a big bracket here, times, see, this would have still been a power of 1, so 7 to the x log base 4 x plus, and these two things would have been gone, plus 9 over ln 4 x ln 4, something like that. I would have left it in that form, but they really didn't. They didn't simplify it too much. So I guess it just depends on who's writing the book and how they want to write it and that type of thing. So some of these you will have to use as they get a little interesting towards the end. So if, give them a shot and see what you can do. But these are our two new theorems right here and right here. And there's nothing spectacular about them, just a little experimentation with the last of the two kind of derivatives, and then we're going to start into something new. All right.